Hello again, it's Professor Albert, here with Lecture 5. Let's learn some econ. So, in short, today we're going to keep working with indifference curves and try to figure out how we can use indifference curves to solve for our optimal bundle given our budget set. So, last time we talked about how we can draw indifference curves. Indifference curves will visualize as these downward sloping pink lines that are increasing as we travel to the northeast, and what's special about these points is every point along a given indifference curve is indifferent to another. That is, all points along L3 are indifferent to all other points along L3. All points along L2 are indifferent to all points along L2. And moreover, all points along L3 are strictly preferred to all points along L2. We are going to combine this with what we did at the end of the last lesson, namely how do we draw our budget set. Well, our budget set is just how much money do we have divided by what combination of goods can we purchase with them. That is, we can purchase up to 25 burritos, up to 50 pizzas, or any combination between the two with equivalent value. Now, the first question I have for you is, given this budget set, given indifference curves that look like this, how can we solve for our optimal bundle? Now, mind you, we don't just have these three indifference curves. In between any two indifference curves you envision, we could draw more, right? In fact, we actually have infinite indifference curves making sort of a topo map extending from the origin all the way out to infinity. So look at the graph and think, for me, where an individual could consume pizzas and burritos in order to maximize their utility. Well, the first thing we're going to do is we're going to try to find the highest indifference curve we can afford. And also, we want to be able to find the highest that we can afford such that we do not spend more than our budget. So let's at least start with the indifference curves we have here. If we look at this indifference curve is the highest drawn. Certainly we could go higher. But why will our optimal bundle not be along this indifference curve? Well, note that we cannot afford this indifference curve. So this one's immediately out. There is no point along L3 that is affordable, so our optimal bundle cannot be there. Next, we might say, well, let's look at an indifference curve like L1. Well, L1 is mostly affordable. We can afford anything from here to here, or in between. Now, certainly we think intuitively that maybe a point like this cannot be our solution because, well, I could have more stuff. However, we'll also note that this point and this point are also suboptimal. Although these spend all of our budget, they do not spend it efficiently. How do I know that? What's a bundle that costs me the same as, say, this bundle, but gives me a higher indifference curve? Well, the answer is anything moving towards the inside. If I start here and I move here, well, I've now moved to another indifference curve that is undrawn that is associated with a higher level of utility. How do I know that? Well, because it's northeast. Moreover, if I were to have stopped at this point, I know that is also not optimal. Why? Well, because I could be consuming along this indifference curve, which is also preferred because it's also northeast. So the question is, when do we stop? When do I stop sliding along this budget set and say that I've consumed the most util-giving bundle that is possible? Students of calculus will note that in situations like this, we want the tangency. What's nice about this is, if I were to consume here, I would note that there would be an indifference curve that is slightly lower than that. I could move up, and I would continue to move towards this point along the budget set. Similarly, if I were at any point here, I could continue drawing parallel indifference curves of higher utilities until I got to this point. So from a limit perspective, this is also very good. Another thing you'll note is tangencies have specific properties that are very appealing. Namely, a tangency is defined as the highest single crossing. If I have any other point in this budget set, it will be crossed by an indifference curve twice. Let's start with our original points. This is on an indifference curve, but this indifference curve is crossed twice. That means there is space between those 2 points with higher utility. If I start at the tangency, like this, there's no interior space to move between. Therefore, we'll say anytime you're confronted with a budget set and you want to maximize your utility, just find the tangency. Why will our optimal bundle always be on the budget line? Well, there's two different types of things we could look at that are not on the budget line. First, we could look at points northeast of this line. What's wrong with those points? Why would we not try to consume a bundle northeast of this blue line? Obviously, those bundles are not affordable. We'd love to afford, say, this, but we cannot. We've run out of our budget. Next, why will we typically consume something along this blue line, not inside this blue line? This bundle is certainly affordable. Why is it unlikely to be optimal? Well, you might note that from lesson 2, we said that more is better is generally assumed. So although this is affordable, we could also afford this. We could also afford this. We could also afford this. Generally, as long as we are not on this blue line, we are not expending our full budget, so there is some slightly more expensive but still affordable bundle that will be strictly preferred because it is northeast of where we started. Next, why will our optimal bundle be at the tangency? Well, as we said before, if we were here, which is not a tangency, you could draw the indifference curve and note that there will be interior space. And if we move along this interior space on the blue line, we're going to get strictly better utils as we move. The only place this is not possible is at a tangency point like E. I will note that, jargon-wise, anytime we invoke a tangency and call this our solution, we have found what is called the quote-unquote interior solution. The reason this is called an interior solution is because the solution is found in the interior of the graph. We could have found solutions along the boundary, i.e. along the x or y axis, where we are limiting one good to 0. But if we are finding a tangency, we are not doing that. We are finding some optimal combination of both goods, both of the goods non-zero. So, for now on, we talk about finding an interior solution. By that we just mean we're going to find the tangency, and we're going to assume that we are not forcing one of the goods' quantities to be 0. The next thing we want to do is think about, well, how do changes in our budget change the optimal bundle? Well, how would my graph change if I were suddenly richer? Think for a moment, draw for yourself how I would change this graph if I found myself with more money. Well, you'll note if I had more money, one thing I can afford is some amount more burritos. Another thing I could afford is more pizza. And the question is, well, at what rate can I exchange these additional pizzas or these additional burritos? Since prices haven't changed, it must be at the same rate. So this line must be at the same slope as the original line, and that suggests to us that we should have parallel shift. Next, along this new budget, how can I find my new optimal bundle? Again, just look for the tangency. And you'll note that this tangency refers to a point northeast of E. Therefore, what can we assume about my preference for this point, we'll call it F, versus my original optimal point E? Well, it must be that this is preferred because it's strictly northeast. So, mo money, mo utils, as they say. Another thing we might ask is, well, what if I didn't personally get richer, right? I have the same amount of dollars Y, but the price of burritos became cheaper. How would I change my graph then? Think it through. Give it a draw. Well, if burritos become cheaper, and I spent my entire budget on pizzas, would that change the quantity of pizzas I could buy? I'd think certainly not, right? Pizzas cost the same amount. If they're $1 each and I have $50, I still get 50 pizzas. Next, if I were to spend my entire budget on burritos, could I afford more burritos? Certainly yes. Burritos are cheaper. By definition, it must be that I can afford more burritos. Therefore, anytime a price changes, it must be that this line rotates. And since burritos are becoming cheaper, it must be that it rotates this way. Again, we should think, should we expect this to make us better or worse off? Well, how do I find my optimal bundle and my maximum utility along the new line? Give it a think. Well, originally it looked like we were tangent at E. Now with burritos cheaper, my budget has rotated outwards, and it looks like I'm consuming at a point somewhere around here. You will note that it is safe to assume that this is a higher utility because I'm along a higher indifference curve. There are points on this indifference curve that are strictly northeast of E, and therefore it must be preferred. You'll also note, interestingly, that this budget line is almost strictly above the original budget line. Therefore, when things become cheaper, it feels like we're getting richer, right? Because we can buy more stuff. And that's good. So for most of this class, our tool will be calculus, right? Graphs like we've been using are really helpful for figuring out where to look for our solutions, but they rarely give us the exact solution. However, graphs will be really useful for us first because they help us characterize exactly what can go wrong. In all the graphs I drew above, 3 things specifically were true. First off, my utility functions as given were convex, that is, they curved upwards. Second, these indifference curves were differentiable, that is, you could take the derivatives of them. If you cannot take a derivative of a function, calculus will not be very helpful for you. How can we make things undifferentiable? Think for a moment back to your calculus knowledge. Tell me what sort of things would cause a function to not be differentiable. You might remember things that are not good are kinks. Other things that are not good are skips. Anytime there's a hole or a kink in your graph, you can't take a derivative. Anytime you can't take a derivative, you're not likely to be able to have any fun when you try to use calculus. Other thing you might wonder is, well, what can happen if I have convex differentiable indifference curves, but they cross the y-axis? You'll see above, these indifference curves seem to asymptote and never actually cross the axis. If they do cross the axis, we get into additional and bigger problems. So, caution. If you're looking at a graph for an indifference curve for a consumer demand problem and you note that the indifference curve is not differentiable, you can't use calculus. The calculus tools that we learned will not help you. Instead, you should rely on the other tools you'll learn to deal with those cases. Similarly, if you observe an indifference curve for utility function for a consumer demand problem, and you note that this indifference curve is either not convex, that is, it's either a straight line or it curves downwards, or these indifference curves cross the axis, i.e. I have perhaps convex things, but they do this, well, in those cases, the tangency you want may not exist in the interior of the graph. And the tangencies you find might not even be the solution. In order to show exactly what happens in cases 1 and 2, we will often look at utility functions that cause this, dependably. We'll call these the usual suspects. And I'm going to show 2 of those now. All right, so first things first, look at the graph on the left and right and tell me what specifically is wrong with these when it comes to the red flags. We said our utility functions should give indifference curves that are convex, differentiable, and don't cross either the x or y axis. Look at the left and right, and you tell me which red flags, could be multiple, are violated in each. So let's start with complements. Does this cross the axis? No. I could draw infinite of these L's. As long as I don't draw the L on top of the axis, it looks like they don't cross. They are parallel to the axes, both vertically and horizontally. Second, are these convex? So the vertical region and the horizontal region is not. That is, this point and this point are not compared with a convex relationship, but these 2 are. As long as we're comparing vertical bits to horizontal bits, it's convex. So maybe it's not strictly convex, but it's definitely not concave or linear. The third thing we should ask is this differentiable? Well, these L's have 2 problems. First off, on the vertical bit, it's not a function, right? It's not past the Malign test. Second, at these points, the limit going from the left and the limit going from the right, which is vertical, they're not the same. So these don't have derivatives. If you try to take a derivative of this, you will not have a good time. So let's see if we can derive some intuition regarding where we would look for maximum utility budget along a function like this. So I've started with just this black line as my budget. The first thing you should ask is, let's look at points A, B, C, D, and E. Which of these points are affordable? After you decided which are affordable, think which of those is best. So It looks like everything but C is affordable. C is northeast of all points on this black line, and therefore it consists of more goods than I can afford. D is also affordable, but it seems like it doesn't spend my entire budget. You'll note, however, that if I move from D to E, I'm on the same indifference curve. Therefore, what must be true about points D and E? That's right, they're indifferent. So although E spends more money than D, it doesn't make me any better off. In fact, there's an unlabeled point, let's call this X, which costs less than E, D, and A, but gives me the same amount of utility. Is there any way to get the same amount of utility as X while spending less money? I'd say no. And the reason I know this is because X is at a vertex. At these vertices, like X and B and C, I am expending the least amount as possible to reach the utility associated with the given indifference curve. Therefore, what point satisfies the two criterion for complements? 1, it's on my budget line, and 2, it's along a vertex. The answer is obviously B. And you can apply this even for budget sets that were not given, right? If I move this budget slightly less, i.e. I lost a little bit of money, where would I look for my utility maximizing budget set? Well, in theory, there'd be another undrawn indifference curve, something like here, and again, I'd be consuming on the vertex. So that's how you solve perfect complements. What will happen on this graph if I increase my budget? What will change? You'll remember from before that we change our budget just by increasing when we get richer, or decreasing as we get poorer, our budget set. So as we move our budget northeast and southwest of points B, you could picture tracing out all of the infinite vertices that connect B and C and beyond. And that is, in short, what happens with perfect complements. So next, let's talk about perfect substitutes. Where is the budget line, here given in black, tangent to any of the indifference curves, either drawn or undrawn? Second, where is my utility maximized? Third, what happens if I increase or decrease my budget set? Give it a think. So first, you might note that this black line is tangent to the pink line at exactly 0 locations. How do I know that? Well, how does the slope of a straight line change as I move left to right? It doesn't. Lines are given by constant slopes. Therefore, trying to find a tangency when you have two lines that have constant different slopes is a little futile. You're not going to find it. Second, let's think about our maximum utils. So I guess we could think about this point, we could think about this point, and we could think about any point in between. So I'll label these A, B, C. Which one of these gives me the most utils, and how do we know? Well, if I look at the graph, this 4 Coke cans bundle gives me 4 utils, or utils equivalent with L4. This 3 Pepsi can bundle gives me the util associated with the L3 indifference curve. Next, note that L3 is strictly worse than L4 because there's points in L3 that are southwest of points in L4. Therefore, it must be that this point is my solution. Moreover, if I were to consume any point along this line, let's say this one, I could draw some undrawn indifference curve, i.e. another parallel line, and note that this line gives me worse utils, lower utils, than I could have at point 4. Therefore, this point must be the solution, i.e. I should just buy 4 cans of Coke and no Pepsi. Now let's look at this graph and think about why that might be. How do I prefer Coke and Pepsi? Well, it looks like I don't care. If I have 4 Coke or 4 Pepsi, I get utilities associated with L4. Therefore, I should buy whichever is cheaper. Looking at this budget line, which is cheaper? Given however many dollars I have, I could either buy 3 cans of Pepsi or 4 cans of Coke. Therefore, it must be that Coke is cheaper, and therefore, when you have perfect substitutes, and your utilities are given by a 1-to-1 ratio, just buy the cheaper good. Very simple. how does this change if my budget increases? Give it a draw on your own. How will I change my graph? Well, if my budget increases, you could picture just another parallel line somewhat to the northeast. Yeah, it looks pretty good. What if the price changes? How will I change my graph? Give that one a think. Give that one a draw. Well, if the price changes, I would just change the slope of the black line. Here I've done kind of the obvious thing, and all I've done is I've changed it such that Pepsi is more expensive to now Coke is more expensive. Could I ever draw a different budget such that I consume a mixture of goods? See, before, when Pepsi was more expensive, I only bought Coke. Here, when Coke is more expensive, I only buy Pepsi. Could I draw this such that I could buy a mixture of the goods? Is there any way? Give it a think. Well, what you might have come up with, well, what if the price is 1-to-1 and my personal utility exchange rate is 1-to-1? Well, if that's the case, what's my optimal bundle? Look at this graph and tell me what my optimal bundle of Coke and Pepsi is. If you said, I don't care, you're right. At all points along my budget, I get the same amount of utils, whatever the utils is associated with L4. Therefore, as long as you spent all of your money, you're happy and you're full of delicious Coke fluids. The last of the quote-unquote usual suspects we'll talk about is quasi-linear. Give this graph a look and tell me what the red flag is here. Now, you might have noticed that quasi-linear is differentiable. I have nice curvy lines that I can take derivatives of at all points. Second, it is concave up. That is, if I were to draw straight lines between any 2 points, I would end up at higher indifference curve. Right? I like combinations of good. It's not like perfect substitutes where I am incentivized to consume one or the other. So what's my other red flag? You'll note these indifference curves cross the y-axis here, and that's a problem. We're about to see why it's a problem, but first let's think about how we would solve this. Look at the graph as given and tell me what my optimal bundle is of burritos and pizzas. Applying the trick we've been doing all lesson, just find the tendency. It looks like this is the best. How do I know? Well, first, it's affordable, i.e. it's on the blue line, and second, any bundle that is on this blue line that isn't this red one is worse because it'll be on a lower indifference curve. And any bundle northeast of this is not affordable. So this is as good as we can get. Next, draw lines like this on your own and then show what happens when I find optimal bundles as I increase and decrease my budget, i.e. I make new parallel blue lines. You will note when you do this, the tendencies trace out a vertical line if you've done this perfectly. That is, no matter how much money I have, increasing from this given value, I'm always going to buy exactly, looks like 25 pizzas. Now the next question is, why are these special? Why are these weird? What is this red flag involving the indifference curves intersecting the y-axis? Why was it a red flag in the first place? Spend a minute changing the slope of your blue lines until you find me something weird. What you'll note that can happen with quasi-linear preferences is if you make this blue line incredibly steep, you will not have a tendency with any purple lines within the graph. If that's the case, we can't use the tendency method. That is, at no feasible bundle, that is with greater than 0 burritos and 0 or greater pizzas, do we have any tendency with our indifference curves. Next, what can we do next? What bundles should we look for? Look at the graph and tell me what affordable bundle gives me the most utilities. Well, the places I would look is, let's look at point E. Let's also look at unlabeled point F. Then let's look at something in between. We'll call that G. Well, if I look at point F, that's totally affordable and is associated with some incredibly low utility undrawn. Let's call this some L0. If I go to point G, it looks like I've got some utility that's better, right? I'm moving along indifference curves that are northeast of where I started. But can I do better? Well, it looks like every point moving north and west along this blue line gives me better and better utilities. Where does it stop? Where can I stop making my utility higher? It looks like point E. Although I could keep drawing this blue line, and I could intersect indifference curves even as high as E, why do those bundles not make sense? Why can't I try to consume, let's call this point X? Well, you'll note at points like point X, they don't make any sense. You can't consume negative pizzas. You'd be in pizza debt prison or something weird. So with quasi-linear preferences based on the slope of your blue lines, it might just be that you have to consume some point along the X or Y axis. These are called corner solutions because you look for them in the corner. So whenever I have utility curves that cross my axes, check one corner, check the other corner, and then if there is a tendency, it's probably that. It just gives you one more thing to check. The other thing that's interesting is, as before we noted that shifting our blue lines north and south didn't change our pizza consumption, the same thing happens when we have corner solutions. Because of the price ratio between pizzas and burritos, it might be that at least for some region of our graph, we just continue to consume 0 pizzas. So let's get into some wacky stuff. We're no longer in the usual suspects. Now here's just some weird graphs we've drawn. Look at the graph, and then tell me 2 things. 1, what red flag do you see? And 2, where would you look for a solution? So this crosses an axis here and here. That's a problem. 2, these are concave the wrong way, right? We like curves that look like this, not curves that look like this. So that's a problem. Are they differentiable? Oh yeah. So the fact that they're differentiable tells me I can find a tangency. Here's a tangency. Is this tangency the solution to my utility maximizing bundle? Where else could I look? Well, I'd look in the corners. E looks to give me higher utility. How do I know? Because E's indifference curve is all strictly north and east of D. So D is not the solution, even though it is a tangency. Humorously enough, D does solve an optimization problem. What does point D do for me? Hint, it is not maximizing my utility. If you noted that D minimizes your utility, you're right. Go to get a cookie. You deserve it. Point D minimizes my utility subject to spending my entire budget, which is an interesting task, but certainly not what I'd try to do when I go to the store. Here's another one. You'll note that this, again, has both red flags, 1 and 2, some solutions that we might try. Tell me what the red flags are and where you'd look for solutions. So first off, is this differentiable? Yeah, looks pretty differentiable to me. 2, do my indifference curves cross axes? Yeah, oh yeah, here and here. It looks like they aren't crossing these axes maybe, but they're crossing here. 3rd, is it concave in the right direction? Well, it looks like it's concave up here. We like that. But it's also concave down here. We don't like that. So this graph, it seems to depend on where we are. So let's look for optimal bundles. The places I would look first are 1, look at your tangencies, and 2, look at your corners. If I look at tangencies, I have 2. I have D, D. Which one of those 2 looks to be better? Well, E is on an indifference curve that is northeast of L1, so that seems to be better than D at least. Next, let's check your corners. Well, this is associated with some undrawn indifference curve that is lower than the one that intersects E. Well, that's no good. And this tangency intersects some indifference curve that's lower than the one that we had at D. So that can't be it. So looking at bundles A and B, D and E, which is best? Well, it looks to be E. It looks like this tangency is the interior solution for our maximum. This is our interior solution for the minimum. And again, that's all we have time for today. Thanks so much, and see you next time.